See, here what we want to do is essentially the problem, if you remember, fx we wanted to write it like this, right? So essentially we wanted to prove inequality like this, the identity like this, yes. And to do that, if you let me do it not a very precise thing, but let me give you an idea of exactly where we are coming from. Okay, so let's say f here is a 2 pi periodic function. So let me put it this way. Given f is 2 pi periodic, yes, 2 pi periodic. Now once this is given, then and of course integrable, we are assuming an integrable, and where is it? In minus pi, yes. So we are just thinking of the function between minus pi and pi. So basically if we integrate both the fx dx between minus pi to pi, and we wanted to write fx in terms of that series, right? So what is the series? It is a naught plus summation an cosine nx plus bn sine nx, right? That's what we wanted to write. So essentially you see n equals to 1 to infinity. We can integrate all these things, right? So we can integrate this thing between minus pi to pi, this whole series with respect to dx. Yes, let's just assume that we can of course do all that. Yeah, now this we can write it at least in this case minus pi to pi a naught dx plus sum. Yes, now of course we don't know if we can do something like this, yes, because the thing is, see, here there is like infinite series, yes. So we don't know if the term wise integration is allowed or not. For now let's just assume that this is allowed. Okay, so assume term wise integration is allowed. Integration is allowed. Okay, allowed. So if we assume something like this, then we can do this integration term by time, right? So it becomes an integral minus pi to pi cosine nx dx plus bn integral minus pi to pi sine nx dx. See, very simple. Yes. Now you see what happens to cosine nx and sine nx between minus pi to pi. We know that this is of course going to be 0, right? And then what we have is you basically have a naught times 2 pi. So minus pi to pi dx is 2 pi. So you have 2 pi a naught is minus pi to pi f of x dx, right? So from here, therefore, hence, let me put it this way, hence a naught is 1 by 2 pi minus pi to pi f of x dx, right? I hope this is clear. Why? Because you can easily see that for any n, sine nx and cosine nx, if you integrate between minus pi to pi, that is going to be 0, right? So this particular terms is going to be 0. You see, these terms are going to be 0. So you will get 2 pi from here. So it is 2 pi a naught, and then you have minus pi to pi f of x dx. I hope this is clear, right? Okay. So now a naught we already got in terms of f of x. So see, fx we wanted to write like this, right? Summation an cosine nx bn sine nx. A naught, out of that we already got in terms of f, because we know what f is and we can integrate it to get a naught. Now we need to find what ans and bns are, right? And this is the place where we are going to use the orthogonality of the trigonometric system. Okay, so let's look at how to find out this property. The second one, that an first, yes, an. Okay, so to do that, to find ans, what we do is this. You see, we multiply. Okay, so let's just let me put it this way. We wanted to write this, right? We wanted to write f of x as a naught plus sum n equals to 1 to infinity an cosine nx plus bn sine nx, right? We wanted to do something like this. Now let's just call this a star for now. Yes. So see, a naught we already got in terms of f, Now we want to get what ANs are. Yes, and again in terms of f. So what we do is we multiply. So first of all, we fix any m. Okay, we fix a m in n. It can be 1, it can be 5. I don't care. Some m. Yes, we fix it and we multiply it by star. Yes, and then we integrate it. Let's see what happens. Yes, so multiplying star on both sides with an, with, let's say, cosine mx. Yes, so this m is fixed. M can be 1, m can be 2, m can be any fixed natural number, right? It does not really matter what m is. You can fix any of that. Yes, so basically we want to find what am is. Yes, and to do that we are going to do this. Yes, so to find am, we are fixing that m and then we are multiplying the whole thing with cosine mx. If you do that, then you see both sides, if you multiply, then this side becomes f of x cosine mx dx, and then this becomes minus pi to pi a naught times cosine mx dx. This becomes 0, right? We have already talked about it. This becomes 0. Okay, plus summation. Again, this term-wise integration, we are assuming that all of this is true. I mean, we can integrate term by term. For now, let's just assume that. Yes. So if we do that, then this is this is n equals to 1 to infinity. Okay, an cosine nx plus bn sine nx times cosine mx dx. Is it okay? We are multiplying it by cosine mx in both sides. So this part is 0, as I told you. The a naught part is 0 because minus pi to pi cosine of any mx dx is going to be 0. So essentially that part is 0. Now you see, if we can take this integration here. Sorry, I have to take the integration here itself also. Maybe I can write it here. Yes, I forgot to write it. So let's just take it there. See, now if I take the integral 1 by 1, so basically an, so let's take it here. An integral minus pi to pi cosine nx cosine mx dx. You see, we know that this is going to be 0 for all m not equals to n, right? Yes, see, cosine nx cosine mx is 0 for all not equals n not equals to m. So from here we are getting the only thing which is remaining is am, and then minus pi to pi cosine square mx dx. Yes, so n equals to m is the only thing which is remaining non-zero essentially. Yeah, and then again this sine and cosine, this part is also going to be 0. You see, sine and cosine, this is always going to be 0 independent of what n and m are. Yes, so that part is 0. So essentially we are going to end up with this minus pi to pi f of x cosine mx dx is equals to am times minus pi to pi cosine square mx dx. Clear? Now you can of course check minus pi to pi cosine square mx dx is going to be pi. Okay, so this is pi times am. Yes, so that will imply am is 1 by pi minus pi to pi f of x cosine mx dx. Yes, now this is any fixed m. It does not really matter what it is. M equals to 1, 2. So for any m, this is true, right? So this is how you find am. So essentially any an is 1 to pi. So this is for any n, right? So therefore an must be written as 1 by pi minus pi to pi f of x cosine nx dx, right? This is for all n greater than equal 1, of course natural number, right? And similarly, what about bn's? Now this you have to do it to find bm. To find bm, what do? You multiply. So you can guess, you can multiply here. Here you multiply it by cosine. Yes, there you multiply it by sine. Okay, so please do it. So do it yourself. You multiply it by, this is a small hint, multiply it by sine mx, and then you can find what is am. To find am, let me put it this way, sine mx for finding am. Yeah. So this I am leaving it to you. Exactly the same sort of thing will happen, and we are just writing what sorry, not AM, BM, sorry, BM, BM. And so essentially I am going to write down what BM you are going to find out, what BN you are going to find out. BN is essentially 1 by pi minus pi to pi. You see, you can guess this part is going to be 0 because sine mx is again going to be 0. This part is again going to be 0 because sine and cosine integral is going to be 0. This part, the only thing which will be remaining is sine square mx dx, right, which will give you pi. So essentially we are going to get something like this. It is f of x sine nx dx. Okay, so this also holds for any n greater than equal to 1. Yes. Okay, so we understood that this is how the formula works. So basically let me put everything together. So this is the Fourier series essentially. Yes, Fourier series. So please remember this Fourier series. What is it? So essentially if f is 2 pi periodic function, yes, 2 pi periodic, and let's say defined on, for now, 2 pi periodic, let's say, yes, and we are basically talking about minus pi to pi, defined on minus pi to pi. Okay, so initially we are only interested in minus pi to pi. Of course they are 2 pi periodic, so it will go on recurring itself. Okay, then f of x, you can write it as a naught plus summation. Okay, now this equals to is misleading. We have assumed that we can write it like this, and then we got some ans bns. This may not be always true. Okay, so this is a small, I will put it in a small star. We'll see that when is it true, when it is not. Yes, so basically this is the representation. We have an cosine nx plus bn sine nx and dx, right? This is n equals to not dx here, sorry, n equals to 1 to infinity. Yes, so fx can be written like this, where what is a naught? If you remember, it is 1 by 2 pi minus pi to pi f of x dx. Okay, and then what is ans? Ans are, how do you remember ans? You see, the first part is 1 by 2 pi, the second part will be 1 by pi. Yes, and then minus pi to pi, of course the integral is same, f of x. Now is it cosine or sine? See, with an there is the cosine thing, so it will be cosine, ans will be cosine nx dx, clear? And bns will be given as, bns will be 1 by pi minus pi to pi f of x sine nx dx. I hope this is clear to you now. Yes, so essentially this holds for almost every x, so you don't have to worry about it. Essentially for any continuous function this is true. Yes, and we are going to do it next. So you understood the idea. If you have a 2 pi periodic function, we can write it in terms of a series where the coefficients, these coefficients, you remember what are a naught, b naught, a naught, an and bns are. So here a naught, ans and bns, they are called, and bns are called Fourier coefficients. Okay, Fourier coefficients of f, coefficients of f. So basically if you represent f in terms of series like this, then this will give you the Fourier coefficients of f. Okay, so this holds for all n greater than equal 1, please remember. Yes, okay, so let's just, of course I'm not going to prove this part, I'm just going to state this part for this course. This proof we are not going to do. Okay, so essentially as I put it, that star is there, right? So essentially when is it true? Yeah, so there is this convergence and sum part, right? So what we explained earlier, if you remember, we wanted to write f of x in terms of this series, right? And then what does that mean? It means that this is an infinite series. Of course, if you can write it as f of x, it means that we are assuming that the series converges. And then if it converges, there is a sum, right? That sum we are assuming it to be f of x. Yes, so that's the idea of it. So but does that really work? So of course it kind of works, we have seen. Yes, and this theorem, the next theorem, will actually guarantee it. Yeah, so let me put it as a theorem. again, the proof, I am not going to do the proof. It is not very, I mean, of course, if you want, you can try the proof. It's not very difficult, but let me just state the theorem. So basically, this is called the representation of Fourier series. Okay, so essentially, can you represent IF in terms of a Fourier series? Representation by a Fourier series. Okay, Fourier series. Okay, let's just understand this. So let f of x be 2 pi periodic. Yeah, of course, we are assuming the function to be 2 pi periodic, right? 2 pi periodic and piecewise continuous. And piecewise continuous. So for our context, what do I mean by piecewise continuous? What I meant is there are finite number of points where it may not be continuous. Okay, so for this at least for this part of this course, we are just assuming finite discontinuous points at most. It may not work. See, it may be continuous everywhere, doesn't really matter, but the maximum discontinuity which we can allow is finite number. Okay, continuity. Okay, finite discontinuity. Okay, finite number of points. So basically, finite discontinuity means there are finite number of points where the functions may not be continuous, except that everywhere it has to be continuous. Okay, in minus pi. If you remember, we are talking about minus pi interval. Clear? Okay, and we are assuming that further assume f of x have a left hand limit. Okay, sorry, left hand derivative and right hand derivative. So basically, both left hand and right hand derivative exist at every point on the interval. Okay, right hand derivative. Okay, at every point of minus pi to pi. Clear? So essentially what we are saying is you have a piecewise continuous function which is 2 pi periodic, and the left hand derivative, right hand derivative has to exist for every point. Yes, that is true. So then the Fourier coefficient, okay, sorry, the Fourier series. So which is the Fourier series? This one. Let's just call it double star. The Fourier series double star. Okay, and let's just call it triple star. These coefficients, yeah, Fourier coefficients. The Fourier series double star converges with the Fourier coefficients. Fourier coefficients. So basically, the series is double star and the coefficients are given by triple star. Coefficients. Let me put it this way: Fourier coefficients triple star converges. So essentially, what am I saying? That under what condition does this converge? Of course, see, if they are all continuous and continuously differentiable. So basically, if you have a 2 pi periodic function which is continuously differentiable, all of this is true. So basically, fx can be written as this for all x. Doesn't matter. But what here I am saying is, for the convergence part of the series, if you want, you just have to have a piecewise continuous function. So basically, there are discontinuities at a finite number of points, and you need to have the left hand and the right hand derivative to exist. That's all. Yeah, and of course, so it converges. Yes, and what about the sum? So basically, its sum is f of x, right? Its sum is f of x. Yes, except at the point x naught. Yes, what is so special about x naught? So x naught is the point of discontinuity. So basically, let's say that, see, if it is always continuous, no issue. If it is discontinuous, there are finite number of points, right? Let's just take at a point where it is discontinuous, x naught. So what happens to the sum? See, if it is continuous, it converges to f of x, no issue. If it is not at that point, x naught, so essentially what happens, the sum, so its sum is f of x except at the point x naught. Okay, where f of x is discontinuous. Clear? Continuous. So essentially what am I saying? If f is, wherever f is continuous, the sum is f of x. Okay. So let's say x is a point where f is continuous, so f of x is the sum. Let's say there is a point where x naught where it is not continuous, then the sum is given by the average of the left and right hand limits. Okay. So let me put it. Also, the sum of the series okay, is the average of the left and the right hand limits, left and right hand limits, right hand limits of f of x at x naught. Okay. So basically what am I saying? If x naught is a point of continuity, sum is f of x naught. If it is not, then the sum is the left and the right hand limits. Okay. So if take that, add it up, divide it by 2, that will be your sum. Clear? So that is basically the representation of Fourier series. So when it converges and if it converges, that is the sum. Okay. So this is the assumptions under which this happens. Yes. So with this, I am going to end this video.